Welcome to Theory of Computation. This is lecture number 32. Well, we have been discussing the theory of NP completeness. As you will recall, what we have done is started collecting these problems that we call NP complete. And all these problems have few properties that they share. First thing is they belong to the class NP. And the second thing is that all problems in NP are reducible to these problems. Therefore, we suspect that these problems are extremely difficult to solve. The other thing that we know about NP-complete problems is that each one of them is reducible to another NP-complete problem. So if you give me two NP-complete problems, I can reduce one into another in polynomial time. Throughout this discussion, whenever we say that a problem is reducible to another problem, what we mean is that it is polynomial time reducible, that the amount of time it takes to reduce one problem into another is bounded by a polynomial only. That means we can convert any NP-complete problem to another one. We started by looking at satisfiability, and then we looked at CNF satisfiability, tree satisfiability. We proved that all these problems were NP-complete. After that, we started looking at some graph theoretic questions. We looked at the clique problem, the vertex cover problem, and the independent set problem, and we proved that all these problems are NP-complete. And we did this via reductions. To prove that SAT was NP-complete, we needed a big theorem, namely the Cook-Levin theorem. After that, our job was much simpler. To prove that a new problem is NP-complete, we could simply take a known problem that we already know is NP-complete and reduce it to our problem. So all we have to do is come up with one reduction, and that shows us that the problem is NP-complete, provided we already can establish that the problem does belong to the class NP. So now our job was much easier. In order to prove NP-completeness, we simply argue that the problem is in NP, and as I've told you, usually this is not a difficult task. The second thing we have to do is take a known NP-complete problem and reduce it to our problem. We looked at a few reducibilities. For example, we can think back and think about the clique question and the independent set problem. Well, what we observed was, if you have a graph and it contains a clique, when you take the complement of the graph, then it becomes an independent set, and vice versa. Thus, the clique and the independence number of a graph and its complement is related. In other words, if G has a clique of size k, then G complement will have an independent set of size k. Thus, coming up with the reducibility from clique to independent set is very simple. All you have to do is simply complement the graph. Most of the reducibilities we looked at were just simple things. If we were to understand the two problems in question properly, somehow the reducibility did stare us in the face. However, today we are going to discuss a NP-completeness result, which I think is a bit non-trivial. It is not obvious how to come up with this reducibility, in the sense that I think in order for a person to come up with this reducibility, they would have to have some original thinking. They would have to be fairly creative. So today's lecture is going to be proving the NP-completeness of a very, very important problem in computer science, which is called the Hamiltonian path problem. After that, once we have proved that the Hamiltonian path problem is NP-complete, we would also briefly discuss and say that the Hamiltonian cycle problem is also NP-complete. Having done that, we will give a few comments on the celebrated traveling salesman problem, which you must have heard of. So that is today's lecture's outline. Let us begin. Let's start by defining what a Hamiltonian path is in a graph. Let G, V be a directed graph. So this graph has vertices and edges are now ordered pairs. So edges have a sense of direction. If I say that I have an edge from a vertex A to B, that doesn't necessarily mean that there is an edge coming back from B to A. So we're talking about directed graphs. V is the set of vertices, E is the set of directed edges or a set of ordered pairs over these vertices. And suppose you're given two vertices, two distinguished vertices S and T, a Hamiltonian path from S to T is going to be a path in this graph that starts at the vertex S, ends at the vertex T, and visits all the vertices of the graph exactly once. So, a Hamiltonian path from a given vertex S to a given vertex T is a path that starts from S, goes to T, and along its way goes through all the vertices in the graph. And of course, since it's a path, therefore no vertices can be repeated. If I give you an arbitrary graph, it may or may not have a Hamiltonian path from the vertex S to a vertex T. For example, suppose if I give you a complete graph, a graph which has all possible edges between its vertices, then clearly any path that visits all the vertices is going to be a Hamiltonian path in this graph. On the other hand, suppose if I give you a different graph in which S belongs to one component of the graph and T belongs to another component of the graph, and there are no edges between these two components, then such a graph will not have a Hamiltonian path from S to T simply because it does not have a path from the vertex S to the vertex T. So the question of having a Hamiltonian path does not arise at all. But in general, if I give you a graph and ask you if there is a Hamiltonian path from S to T, that is a non-trivial question. For that, you will have to examine the graph very closely and know a lot about the graph, maybe perform an exhaustive search before you can be sure if there is a Hamiltonian path from the vertex S to T. In order to understand this problem more thoroughly, let's look at a few graphs and see whether they have a Hamiltonian path from a given vertex S to T. So let us now look at the graph that is shown to you on the screen. Does this graph have a Hamiltonian path from S to T? So look at this graph once again and see if you can find a Hamiltonian path from the vertex S, which is marked in this graph, to the vertex T. Well, this graph does have a Hamiltonian path from the vertex S to T, and in order to show you this path, what we have done is we have drawn the edges of this path with bold arrows. So if you look at this new figure, which is a figure of the same graph, you realize that there is a Hamiltonian path from the vertex S to T, which is drawn in bold arrows because it goes through all the vertices of the graph exactly once, and it starts from the vertex S and ends at the vertex T. So that's what a Hamiltonian path is. In order for you to find such a Hamiltonian path, you will have to examine the graph very closely. So one suspects that this would be a hard problem. Let us now take this problem and define a language from it. As we do in the theory of NP completeness, what we want to do is convert this into a yes-no question. So let us define Ham path to be the set of all graphs and pairs of vertices S and T. Actually, it's the set of encodings of all graphs and pairs of vertices S and T such that G has a Hamiltonian path from the vertex S to the vertex T. Thus, the computational question is that given a graph G and two vertices S and T, does there exist a Hamiltonian path from the vertex S to T? So if you were to come up with an algorithm for solving this problem, your algorithm will take as an input some description of a graph, and it will then take two vertices S and T. Then it will somehow analyze the graph and report whether the graph has a Hamiltonian path from the vertex S to the vertex T. The first thing to ask is whether this problem, the Hamiltonian path problem, is in the class NP. remember, in order for us to show that a problem is in the class NP, all we have to do is to give a verification algorithm. So if somebody comes up with a graph G, what the question we have to ask is, if the graph has a Hamiltonian path from S to T, can we give a easy verification algorithm which verifies that a graph has a Hamiltonian path from S to T? Well, how will you convince somebody? How will you prove to somebody that a given graph has a Hamiltonian path from S to T? Well, as usual, the most obvious way to convince somebody that a graph has a Hamiltonian path from S to T is to actually show them the Hamiltonian path. If I show you a Hamiltonian path, or if I describe to you a Hamiltonian path from which exists in a graph from S to T, then it is very easy for you to verify that the path that I am talking about is indeed a Hamiltonian path. All you will have to do is to check that the first vertex of this path is S and the last vertex of this path is T. Then you will check that each vertex of the graph actually appears exactly once in a path, once in this path, which can be done very easily by an algorithm in polynomial time. Lastly, what you would do is you would check whether this list is indeed a path or not. You would check if the first vertex and the second vertex form an edge. Then you would check if the second vertex and the third vertex form an edge, and so on for all the vertices that exist in this path. This way you will be able to verify if the given path is a path in your graph or not. Thus, this problem is in NP. As I've told you, usually it is not hard to show that NP-complete problems belong to NP. That's just a routine exercise. What is difficult to show is that they are NP-hard, that there is some NP-complete problem which actually reduces to them. So that's what we are going to try to do for the rest of this lecture. We will actually show that the Hamiltonian path problem is NP-complete. The way we will show that the Hamiltonian path problem is NP-complete is by showing that 3-SAT is polynomial time reducible to the Hamiltonian path problem. Since 3-SAT itself is NP-complete, consequently the Hamiltonian path problem is also NP-complete. So what we will do is come up with the reducibility from the 3-SAT problem to the Hamiltonian path problem. And since we know that 3-SAT is NP-complete, that would show to us that the Hamiltonian path problem is also NP-complete. Now, this reducibility is not the most obvious one, and I think the reason for that is these two problems are not closely related to each other at first sight. If you think about satisfiability, that has to do with Boolean assignments. You have 2 to the n possible assignments and you're looking for one that would satisfy your formula. On the other hand, Hamiltonian paths in graphs seem to be completely different structures that don't seem to have anything to do with Boolean assignments. So relating them is going to take some ingenuity, and that's what's going to be the heart of this proof. But let's first try to understand what do we have to do in order to come up with this reducibility. Well, given a Boolean formula phi, what we want to do is we want to map this Boolean formula phi to some graph such that the Boolean formula phi is satisfiable if and only if G sub phi has a Hamiltonian path. If we can do that, furthermore, if we can compute this graph G sub phi from phi in polynomial time, we will have a reducibility. So somehow we have to look at this Boolean formula phi and from there magically come up with a graph such that it will have a Hamiltonian path if and only if the original Boolean formula was satisfiable. So this is our goal. and our goal is going to be to come up with a definition of this graph G sub phi. Given a Boolean formula phi, we will define a graph G sub phi and two vertices S and T in this graph such that G sub phi has a Hamiltonian path from the vertex S to the vertex T if and only if the Boolean formula phi is satisfiable. Once we do that, it's going to be fairly obvious that G sub phi is computable from phi in polynomial time, and that would be our reducibilities. So let us take a formula phi, and this formula phi is in C and F. So this formula phi is equal to C1 and C2 and C3 and Cm, where C1 up to Cm are clauses of this formula, and x1, x2, xn are variables in phi. We will now describe how to construct this graph G sub phi. So we have a formula phi which has m clauses C1 up to Cm, and it has n variables x1 up to xn. What we will do is we will define a graph by looking at this formula phi. The first thing that we are going to do is for every variable we'll make a diamond-like structure in our graph that is shown to you in this figure. So for each variable xi, we will create a diamond-shaped structure as shown in this figure. This figure shows the diamond-shaped structure that has been created for each node xi. As you can see, there is a diamond-shaped structure for each variable xi, and from the first vertex we can either go to the left or go to the right. And then we can also travel along in this direction, or we can go this way and travel along in this direction. So if we go on the path like to the right, to the left, and then move right, we will call this a zigzag path. And if we go the other way around, we'll call that a zigzag path. Now what we'll do is for each clause, we will create a vertex and label it Cj. So for every clause, we will create a vertex C sub j. For every clause C sub j, we'll create a vertex and label it with that clause, so that vertex would be labeled C sub j. These would be called the clause vertices in our graph, and they are separate from the diamond-shaped structures. Now what we will do at the end is add two special vertices S and T to this graph. S would be added at the top of this graph, and T would be added at the bottom of this graph. Now what we need to show you is how to connect the vertices in the diamond-shaped structures to the clause vertices. Each xi has two vertices for each clause Cj, so the diamond vertices are as follows. So if we zoom in into the diamond-shaped structure, we realize that there are 2m vertices there, and there are two vertices for each clause. So if you look at clause C2, you would find in each diamond-shaped structure two vertices which are labeled C2 left and C2 right. So this is how we will have the vertices inside these diamond-shaped structures. As you can see, these vertices are paired up. Two vertices each correspond to a clause. We label them C sub jl and C sub jr by calling them left and right vertices. Now we explain how these diamond-shaped structures will interact with the clause vertices. To connect the clause vertices in a diamond-shaped structure and the clause vertices, here is the rule. Suppose the variable xi appears in the clause Cj. So we look at a variable xi, and let's say it appears in the clause Cj. To take a concrete example, you can think of vertex x1, and let's say it appears in the third clause C3. Then what will we do? We will connect the vertex in the diamond for xi that is labeled C sub jl with the clause vertex Cj. We will also connect the clause vertex Cj with C sub jr. Formally, we'll be adding the following edges. The first edge is C sub j sup l, comma C sub j, and the second edge is C sub j, comma C sub j sup r. Here is a picture of this. As you know, this graph is a directed graph. Therefore, all the edges in this graph have a direction. Now, here is the idea. Suppose I look at the diamond of a vertex x1 and it appears in clause number 3. Then on this diamond, I have two vertices that are labeled C3 left and C3 right. I add a directed edge that would allow me to go to the third clause vertex, and then I add a directed edge that allows me to come back to the next vertex, which is labeled C sub 3 sup r. So I have an edge going to the clause vertex and one coming back. So, and these edges have a direction. That's the rule. Well, there is another rule which allows us to add edges between vertices in the diamond to the clause vertices. That is, what happens is if x sub I appears negated in the clause C sub j, then we add these edges backwards. This finishes the construction of the graph. Let us look at a complete picture for the following formula. So here on the screen, you have a Boolean formula phi, which is given by these clauses and variables. And what we want to do is we want to look at a complete graph that would be made using this recipe or using description that I have just given you. So this is the formula, and now let's have a look at the graph and see it has all the ingredients that we talked about. So in this complete picture, we have the diamonds which correspond to all the variables in the Boolean formula, and we also have the clause vertices. And as you can see, between the clause vertices and the diamond structures, there are edges going across, and they go across depending on whether a variable xi appears in that particular clause or whether it appears in a negated form in that clause. If it doesn't appear, then there are no edges going. So this is how this graph G sub phi is constructed. If you think about the construction of this graph, that is extremely bizarre. It's extremely strange. Why would somebody think of making up a graph like that and defining it in such a weird way? Well, before we ask that question, let's ask ourselves another question which we'll come back to at the end of this discussion is, can we compute this graph from phi in polynomial time? And if you think about it for a little while, the answer is yes. This graph is not hard to compute because I can just read the formula and without doing any difficult calculations, just compute this graph G sub phi. What can we say about this graph? Well, I will convince you of a very interesting thing. That is, that suppose the formula phi is satisfiable, then this graph is going to have a Hamiltonian path from S to T. On the other hand, this statement, the converse of this statement is also true. Namely, that if this graph has a Hamiltonian path from S to T, then phi must be satisfiable. Thus, phi is satisfiable if and only if G sub phi has a Hamiltonian path from S to T. So this graph is what we are looking for. The map taking phi to G sub phi is the reducibility we have been looking for. Actually, if we ignore the clause vertices, then finding a Hamiltonian path in this graph from S to T is very easy. We can go through each diamond in two ways. Well, let's look at a picture of a diamond, and what we can do is there are two ways to go through a diamond. We can start from the vertex, go to the left, and then traverse all the edges of this diamond and come back. Let's call that a zigzag path or a left to right path. On the other hand, we could move in the other direction, go through all the vertices of this diamond and come back to the next vertex, and let's call that a zigzag path. Thus, going through each diamond, I have two choices. I can either go this way or I can go that way. either I can take a left-right path or I can take a right-left path. Well, remember there was one diamond for each variable in the Boolean formula. Each variable can be set to either true or false. And from the diamond, through the diamond of each variable, I can either go in a zigzag path or the zag-zag path. Well, that's the connection. Whether we go through a diamond through a zigzag path will correspond to setting this variable to be true, and if we go through this diamond in a zag-zag path, that would be corresponding to setting the variable false. So if you think about it, if I just forget about the clause vertices and think about how many ways I can have a Hamiltonian path in the rest of this graph, there are 2 to the n ways. At every diamond, I can either choose to go in a zigzag fashion or a zag-zag fashion. So there are 2 to the n ways of making Hamiltonian paths in this graph. On the other hand, there are 2 to the n variable assignments. Thus, the 2 to the n assignments corresponding to traversing the diamonds in 2 to the n possible ways. Let us say we have the assignment x1 equals true, x2 equals false, and x3 equals true. Then we will traverse this graph as shown in the figure. So let's look at this figure and see how we will traverse the graph. Well, in the first diamond, we go in a zigzag fashion, but in the second diamond, since x2 is set to false, we go in a zag-zag fashion. And the third diamond, since x3 is true, we once again go in a zigzag fashion. So, the variable assignments correspond to Hamiltonian paths in this graph if we were to ignore the clause vertices. Well, now, the clause vertices will come in the picture and we'll see how they come in the picture. Note that if we're traversing the diamond for xi from left to right, then we can pick up the clause Cj if xi appears in Cj. This is due to construction. This is because if xi appears in Cj, we have added the edge from Cjl to Cj and back to Cjr. Thus, when we are going through the diamond for xi, we can go and pick up the clause Cj and come back to the next vertex and keep traversing the diamond in the same direction. But this we can only do if xi appears in the clause Cj. So if xi appears in the clause Cj and we are going in a zigzag fashion through the diamond of xi. On the other hand, if xi bar appears in the clause Cj, then this method will only allow us to pick up the clause Cj if we are traversing the diamond for xi in a zag-zag fashion. Let's look at the figure. In this case, we're going through the diamond in a zigzag fashion and we're picking up the clause because we have an edge from Cj sup L to the clause vertex Cj and back to the vertex Cj sup R, and we can continue our journey in the zigzag fashion. Note that if we are traversing the diamond for xi from right to left, then we can pick up a clause Cj if xi bar appears in Cj. This again is by construction. In this case, remember we have the edges reversed. So we have an edge from Cjr to Cj and back to Cjl. Thus we can continue our journey in the zag-zag fashion. This way, if we want to pick up a clause Cj, we realize that at least one of the literals in that clause must be satisfied. Suppose we have a clause and xi appears in it and xi is set to be true. Then we will be traveling through the diamond for xi in a zigzag fashion and we can pick up that clause Cj. Suppose that some other variable xi prime appears in Cj negated. So xi prime bar appears in the clause Cj. Now if xi prime is set to false, then we would be traversing xi prime in a zigzag fashion, and we can pick up the clause Cj. Thus, if we have an assignment that satisfies a particular clause, then we can pick up that clause along the Hamiltonian path that we have made from the vertex S to the vertex T. Now, suppose we have satisfying assignment for phi, which satisfies all the clauses. Then we can pick up all the clauses by traversing the graph in a way specified by the satisfying assignment. So all we do is we take the satisfying assignment, we traverse the graph in a zigzag or a zigzag fashion, and every time we have an opportunity, we pick up a clause vertex. Thus, this would be a Hamiltonian path which will start from the vertex S and end at the vertex T. It would have also picked up all the clause vertices. So it will be a Hamiltonian path in the entire graph. So if phi is satisfiable, then we can do the following. We take a satisfying assignment of phi, we start from S, we traverse each diamond for xi in the order specified by the assignment. If xi is set to true, we go from left to right, that is, we go in a zigzag fashion. If it is set to false, we go from right to left. Along the way, we pick up any Cj that has not already been picked up. This yields our Hamiltonian path from the vertex S to the vertex T. Thus, if you give me a formula phi and I can find a satisfying assignment for this formula, then I can go in this graph G sub phi and find a Hamiltonian path from the vertex S to the vertex T. So what we have proved is the following lemma. If phi is satisfiable, then G sub phi has a Hamiltonian path from S to T. So this is one half of what we wanted to prove. What we want to prove is if phi is satisfiable, that implies that G sub phi has a Hamiltonian path, and the converse of that is true also, that if G sub phi has a Hamiltonian path from S to T, then phi must be satisfiable. Let us do the remaining half of this lemma that we want to prove. To prove the theorem, we have to ask ourselves what kind of Hamiltonian paths can occur in G sub phi. Now, what we want to do is we want to prove that if someone finds a Hamiltonian path from S to T in G sub phi, then phi must be satisfiable. And so in order to do that, what we have to do is stare at this graph G sub phi and try to understand how a Hamiltonian path can exist in this graph. Well, it has to start from the vertex S, then it has to end at the vertex T, and along the way it has to pick up all the vertices in this graph G sub phi. What we will do is we will call a path normal if it starts from S, ends at T, and here we're talking about Hamiltonian paths only, and it goes zigzag or zigzag along each diamond while picking up some clause vertices. So a normal path will go through the diamonds either in a zigzag fashion or in a zigzag fashion. So a normal path will naturally define an assignment. And we will say that if a normal path is Hamiltonian, then that gives us an assignment that satisfies phi. However, for this plan to work, we must convince ourselves that there are no non-normal Hamiltonian paths in this graph. Then all Hamiltonian paths that start from S and end at T must follow this recipe. Can we do that? Let's proceed with doing that. The first thing to notice is that if G sub phi contains a Hamiltonian path, it must be normal. Let us argue that a non-normal Hamiltonian path cannot occur. A path must start from the vertex S and go through the diamond vertices. Once it is on an xi, it can either go left or right. Let us argue that if it goes to the left, then it must go through all the vertices of the diamond while picking up some clause vertices from left to right. So what we are trying to do is we're trying to say that if from the vertex xi, if it moved left, then it must pick up all the vertices that come in that diamond. And while doing that, it may pick up some close vertices. So it would be a zigzag path. If we can prove that, a similar argument will show that if from xi it comes to the right of the diamond, then it must pick up all the vertices from right to left, and it must be a zigzag path. We will do only one half of the argument, the other half is fairly similar. Well, let's examine this path and see what can go wrong, and argue that if something goes wrong, if the path tries to do something different, then it can never be extended to a Hamiltonian path. Suppose the path is going from left to right. Of course, if a path is going from left to right along a diamond, it can never come back because it's already visited. If a path goes along a diamond from left to right, it can never come back if it is a Hamiltonian path, because a Hamiltonian path is not allowed to repeat vertices. So this path must keep moving forward. Well, what can it do? It can jump from there to some close vertex. Now, if it comes back to the next vertex, then it's just a normal path and it will continue going. So the only thing that can go wrong is that it comes down, goes to a close vertex, and jumps to some other diamond. Can this happen? We argue that this cannot happen if we are talking about a Hamiltonian path. Any Hamiltonian path from S to T cannot do that, because we will not be able to extend this path to a Hamiltonian path. An ordinary path in the graph can do it, but not a Hamiltonian path. So suppose the path is going from left to right and leaves and collects a close vertex Cj. It must go to Cj from Cj sub L. That's the only way to collect a close vertex Cj if it's moving from left to right. We argue that it must immediately return back to Cjr, which will say that this path is acting normally. If it does not, then how can the path ever reach C sub jr? Because this path has to eventually hit all the vertices, since it's a Hamiltonian path, so it must eventually reach the vertex C sub j sup r. How does it do that? Let's think about it. The only edges coming to C sub jr are from C sub jl and from C sub j plus 1l. This path did not take the edge from C sub jl, so it must reach C sub jr via C sub j plus 1l. But then this path is stuck and it cannot reach T. Well, this is not very hard to understand. Let's see, this is the vertex C sub jl. The path came here and went to some other close vertex. Now this is the vertex C sub jr. If the path doesn't immediately come back to it, then it has to pick up this vertex somehow. But this vertex has only one edge coming from this side and only one edge coming from this side. This edge was not taken by the path. Therefore, this vertex C sub jr can only be reached this way. But then this path is stuck there because both the edges go to vertices which are already visited by the path, so this path can never reach T if it is a Hamiltonian path. Thus, every path in this graph, every Hamiltonian path that starts from S and goes to T must be a normal path. Let's illustrate this argument by a picture. So as you can see, this picture shows you how the situation that we have said leads to an impossibility. This actually shows us that all Hamiltonian paths in this graph from S to T are normal. And this shows that these paths correspond to truth assignments as follows. For a zigzag path through a diamond xi, we set xi to be true, and for a zigzag path through a diamond xi, we set a xi to be false. Now, what we are doing is, we're saying, if you give me a Hamiltonian path in this graph G sub phi, then it must be a normal path. In a normal path, through each diamond, the concept of whether it goes zigzag or whether it goes zigzag is well defined. When I look at a diamond, I can just check whether the path went zigzag or whether it went zigzag, and that gives me a truth assignment. Now, that truth assignment, if the path is a Hamiltonian path, must be a satisfying assignment for the formula phi. Why is that? Because we've seen that in a normal path, you can pick up a clause vertex if and only if that variable is satisfying that clause. And if that happens and you're picking up all vertices, that means that that assignment must be satisfying all the clauses of phi. Thus, what we have shown is that G sub phi has a Hamiltonian path if and only if phi has a satisfying assignment. Now, it is clear that if a path picks up Cj while going through the diamond xi, then the assignment of xi makes Cj true. Thus, the Hamiltonian paths in G sub phi correspond to satisfying assignments of phi. So, we have proved that if phi is satisfiable, then G has a Hamiltonian path from S to T, and vice versa. That if G sub phi has a Hamiltonian path from S to T, then phi is satisfiable. This shows us that f of phi defined by G sub phi is a reducibility from a Hamiltonian path problem to the satisfiability problem. And if you think for a moment, you will realize that this is actually a polynomial time reducibility. Given phi, it's very easy, very simple to compute G sub phi. What we can do is we can just examine phi and look at all the variables that appear in there, all the clauses that appear in there, and we can make this graph G sub phi. And the edge connections are made by just looking at which variables appear in which clauses and which variables appear negated in which clauses. That's all the information we need to compute G sub phi from phi. And this shows us that the Hamiltonian path problem is NP complete. Now, the proof of NP completeness of the Hamiltonian path problem is finished. But let's think about a few things before we go any further. What we want to do is, what has this reducibility shown us? Well, we have come up with a method such that from a formula phi, we can make a graph G sub phi. And if the formula phi was satisfiable, G sub phi will have a Hamiltonian path from S to T. If the formula G sub phi was not satisfiable, G sub phi will not have a Hamiltonian path from S to T. Now note that we have not shown how to find a satisfying assignment for the formula phi. Neither we have shown how to find a Hamiltonian path in the graph G sub phi. What we are saying is we can convert one problem into another problem in polynomial time. So we are saying that the relative complexity of these two problems is related by a polynomial. We're not saying that individually any of the problems is easy to solve. What we're saying is we can convert one problem into another in polynomial time. You must remember that every time you do a reducibility. You must remember that when you reduce a problem A to a problem B in polynomial time, neither do you show that A is polynomial time solvable, nor do you show that B is polynomial time solvable. What you're saying is A can be converted into an instance of B, an equivalent instance of B in polynomial time. So this shows us that the Hamiltonian path problem is NP complete. Thus, it's highly unlikely to have a polynomial time algorithm. Now, let us look at a very related problem, a problem that is not very different from the Hamiltonian path problem, and discuss its complexity. A more natural and celebrated problem is what is called the Hamiltonian cycle problem. Recall that a Hamiltonian cycle in a graph is a cycle that contains all the vertices of the graph. It is very closely related to what is called the traveling salesman problem. That problem is also NP-complete. So this problem, the Hamiltonian cycle problem, is also NP-complete. And that's your homework to prove. Well, how are you going to prove that the Hamiltonian cycle problem is NP-complete? Let me get you started on that. Well, first thing you will do is you will prove that the Hamiltonian cycle problem belongs to the class NP. And by now, you should be experts at doing that, and it should only be a 4 or 5 line argument for you to write. After that, you would want to prove that the Hamiltonian cycle problem is actually NP-complete. Well, in order to prove that it's NP-complete, you will have to take a known NP-complete problem and reduce it to Hamiltonian cycle problem. Well, the Hamiltonian path problem was not easy to prove that it was NP-complete. In fact, I'm still marveling at the reducibility that showed that it was NP-complete. So someone had to be very creative to come up with that reducibility. Will you have to do the same for the Hamiltonian cycle problem? Well, the answer is no. You have a problem which is very close to the Hamiltonian cycle problem, then you now know is NP-complete, namely the Hamiltonian path problem. So you should just try to reduce the Hamiltonian path problem to the Hamiltonian cycle problem, and that will show you that the Hamiltonian cycle problem is NP-complete. Now, let's discuss another very, very celebrated question, which is called the traveling salesman problem. The traveling salesman problem is the following problem. A traveling salesman wants to start from his home and visit all the major cities in a district and come back to his hometown. Given that he has found out about all the fares from each city to every other city, can we find the cheapest way for him to make his tour? So the traveling salesman problem has a very practical flavor to it. Suppose you wanted to visit certain cities of a country and you found out all the fares of all the airlines, and let's say from every city to every other city, can you find the cheapest way to tour the whole country and come back to where you started from? So if you think about the traveling salesman problem, it's not a yes-no question. It's not a decision problem. It's an optimization problem. The traveling salesman problem in the language of graph theory says that now you have a directed weighted graph where edges have been given weights or costs. And what you're looking for is the minimum weight Hamiltonian cycle in your graph. And the question is whether this can be done in polynomial time or not. Well, this is an optimization problem, so we can't really technically talk about the NP completeness of this problem. The class NP is a class of only decision problem. It's a class of languages, so it does not contain optimization problem. Nevertheless, we can prove the following theorem for this traveling salesman problem. The TSP is not a yes-no question, it's an optimization question. It not only asks us to find if a Hamiltonian path exists, but find one with the least cost. So intuitively, this problem seems to be harder than the Hamiltonian cycle problem. We can make this intuition precise by proving the following theorem. The theorem says that if the TSP has a polynomial time algorithm, then P would be equal to NP. Thus, finding a polynomial time algorithm for the TSP problem will have the same consequence as finding a polynomial time algorithm for any NP complete problem. So, The reason I'm mentioning TSP is because Jack Edmonds had conjectured that there is no polynomial time algorithm for this problem, and thereby conjecturing that P is actually not equal to NP. So in the next lecture, we will also discuss the NP completeness of another very interesting question, which is called the subset sum problem. This problem is not going to be from graph theory, and the reducibility is going to have a completely different flavor to it. I'll see you next time. Thank you and goodbye.